if you go outside and you drop some objects, they will accelerate towards the ground. They'll go faster and faster and faster until they hit the ground. And there are a lot of factors that affect how quickly that object you drop will pick up speed. Some objects will pick up speed quickly, some will pick them up more slowly. So let's discuss some of those factors. One thing that people often note is the mass of an object makes a difference. For example, if you drop a balloon filled with air, it'll pick up speed pretty slowly. If you drop a balloon that's filled to the same size but of water, giving it much more mass, it'll pick up speed much more quickly. Another thing is the area of the object. A good example here is if you take a sheet of paper and you drop it, it'll sort of slowly flutter towards the ground without picking up speed very quickly. If you take that same sheet of paper, you crumple it into a ball first. So now you have something that has the exact same mass as before, but a much smaller area, and you drop it, it'll pick up speed much more quickly and reach the ground faster. Those are sort of the 2 points that are most obvious to people, that people have the most experience with. But there are other points too that matter. One is elevation. So if you are on the ground, whatever city you live in, likely closest to sea level, and you drop an object, it'll accelerate downwards and hit the ground. But if you, say, go up to the top of Mount Everest, and then you take that same object and you drop it, do the same experiment, it'll take a little bit longer to hit the ground. It'll accelerate not quite so quickly. The difference is tiny, like maybe 1%. But there is a difference. So elevation matters. The further you are away from Earth, the weaker gravity is, and the slower things will accelerate. So if we want to talk about going further away from Earth to where this gravity is weaker, we can go further than the top of Mount Everest. We can go to the moon, or we can go to another planet. Even staying on Earth and staying at the same elevation and keeping the area and the mass of the object fairly constant, there are still places we can go that will change the acceleration of the object when we drop it. So the thing that's pulling on the object, that's causing it to accelerate, is Earth, is the ground beneath it. And the reason Earth pulls things down more quickly than, say, the moon does is because Earth has more mass. But there are parts of Earth that have more mass than other parts. If you're standing on the ground above a place where there's a big deposit of a really heavy ore, maybe gold or iron or something like that, those things are quite heavy. And so the gravity will be a little bit stronger in that area than if, say, you're standing above a place where it's just kind of a bunch of fluffy dirt beneath you. So what the Earth is made of beneath you also affects how fast things will accelerate when you drop them. Again, this difference is tiny. We're talking like 1% or less, but it makes a difference. Another thing that even matters is how close you are to the equator. So this one's a little bit hard to demonstrate, but imagine you have a globe in front of you. One of the things that globes do, one of the things they illustrate well, is that the Earth rotates. If you're on the equator, it's sort of like being on the outside of a merry-go-round. That's the part where the spin of the Earth is making you travel the fastest. And if you stick your finger on one point of that globe, right on the equator as the globe is spinning, you'll notice that your finger is always changing direction. It's going in this circle. So if you drop something there, the ground beneath it is sort of traveling in this circle. It's always curving away from where you drop the object from. So if you drop an object on the equator, yes, it accelerates towards the ground, but the ground is also sort of turning and moving and accelerating away from it. So when you drop an object on the equator, not only does it have to sort of get back to the height it started from, it has to go a bit further than that because the ground is curving and is moving away from it. So in that sense, it seems like your acceleration is a bit less if you're on the equator because it takes longer for you to reach the ground. In contrast, if you're at one of the poles, where the spin of the Earth just kind of rotates you in a tiny circle but doesn't really give you much speed, and you drop something, the spin of the Earth does not affect it. Because at the North and South Pole, the Earth isn't really turning away from you or diving away from you in the same way it is on the equator. So, this is a lot. If we had to account for all these things every time we tried to figure out how long it was going to take an object that had been dropped to hit the ground, it would be unmanageable. If I said, I dropped this ball from a height of 10 meters, how long does it take to hit the ground? And you had to ask, okay, well, first of all, what's the mass of the ball? What area does the ball have? What's the elevation you were at? I know you were 10 meters above the ground, but how far were you above sea level? We can generally assume we're on planet Earth, but not always. You'd want to ask what the Earth was made of beneath me. Is there a big mine underneath me? How many tunnels are drilled in that mine? And what is your latitude when you're dropping this ball? Are you close to the equator or are you far away from it? If you had to ask all those questions in order to give me an answer, it would become a bit unwieldy. Fortunately, almost all of these things make basically no difference most of the time. So we're actually going to get to a point where we can answer questions like that. I drop a ball from 10 meters, how long does it take to hit the ground? And we can answer them pretty easily. And that's because we're going to know which of these things we can ignore. And often being a good physicist or being a good engineer is not always about knowing how to solve for every single detail and knowing how to account for every single detail. It's about figuring out which details you can ignore and which ones are important. So, here's what I want you to ask yourself when you're looking at an object that is falling. Question 1, is it close to the surface of the Earth? So if an object is close to Earth's surface, if an object experiences negligible air resistance, and if the object feels no force except gravity, if all that is true, then we know what its acceleration will be. It doesn't depend on how big the object is. It doesn't depend on how much mass it has. If all of these things are true, then we know the acceleration of the object will be 9.8 meters per second squared down. Remember, this down, we're talking about acceleration. So this down is not because the object is moving down. This is because the acceleration is down. So the pull is down. Even if an object is moving up, as long as these three things are true, its acceleration will be down. Okay, so let's look at these one at a time. Close to the surface of the Earth. Basically, if you can see ground, or if you can touch ground from where you are, this is a pretty, then I consider this criterion met. Whether you're at sea level or whether you're at the top of a mountain, we already said going up Mount Everest made a difference, but it was tiny. If you can touch ground from where you are, you're considered close to Earth's surface. If you're, in a satellite zooming around Earth, now you're getting high enough that might make a difference. But if you can touch ground from where you are, you're close to Earth's surface. Air resistance being negligible. So there's always a little bit of air resistance. But air resistance is only really noticeable for things that take up a lot of area or are going really, really fast. So when we talked before, up here, about a water balloon and a regular balloon, and how the water balloon accelerated faster because it had more mass, that was actually because of air resistance. A regular balloon feels a lot of air resistance on it that slows it down, that stops it from speeding up. And if you put more mass in it, it sort of overcomes that air resistance. Similarly to the two pieces of paper we dropped, the regular sheet and the crumpled up piece. The regular sheet had a lot more area, which meant there was more stuff for the air to push against, so the air slowed that piece of paper down. But if we're talking about an object where air resistance is negligible, so it's not a big light balloon that takes up a lot of space, it's not a sheet of paper that takes up a lot of space, then changing the mass and changing the area would actually not make any difference at all. So in which cases is air resistance negligible? Well, almost all the time. If you're talking about something really light that takes up a lot of space, like a balloon or like a piece of paper, then we have air resistance, or we have a lot of it, and we can't neglect it. If you're talking about something going really fast, like hundreds of kilometers per hour, then okay, there's going to be a lot of wind pushing against it. Air resistance will make a difference. But in basically all other cases, air resistance is pretty small. We can ignore it. It's negligible. And that's because the air is very, very thin. It's not very dense. Moving through air is pretty easy compared to moving through water or running into a wall. Okay, and then this part about feeling no force except gravity. Well, if something is touching the ground or it's touching another object, it gets some support or it gets a force from that object or from the ground. And that can mean it'll move differently than if it only had gravity to contend with. Or if something has, a jetpack or rockets on it, that also provides a force. But if you just got an object without any rockets or propellers on it, it's not touching anything, it's just in the air, either going up or going down, nothing else is touching it, then we can say it feels no force except gravity. Okay, so if those conditions are met, the acceleration of any object, doesn't matter how big it is, doesn't matter what its mass is going to be 9.8 meters per second squared down. Now, a couple of the things I noted here is that, there are places you can go on the Earth where this is slightly different. So if you're at the equator, it's more like 9.77. if you're at the poles of the Earth, it's more like 9.83. But notice all of those numbers, if you round them to 2 sig figs, give us 9.8. So if we want more accuracy than that, we need to know kind of where we are on the Earth. But if we're happy with 2 sig figs and knowing them exactly, 9.8 is good. Okay, so let's do an example here. A football is kicked straight up in the air at 15 meters per second. First question, how high does it go? So I'm going to draw a quick diagram here. Okay. And here is, I'm going to do a quick stick figure. It was just kick the football. And it's left their foot, so they're not going to give it any more speed. It's going to go up in the air, and then it's going to come down. Now, one thing to point out is what this football would actually do if you kicked it straight up is it would go up and then back down along the same path. It wouldn't kind of shift over to the right like this. But the reason I just draw it like that is so we can clearly have sort of separate diagrams that show us the way up and the way down, because we want to look at those separately, even though they would occur right on top of each other at the same place. Okay, so let's use some kinematics to look at this. I want to know VF, VI, A, D, and T. And if I'm going to solve the problem this way, I need to know where my initial and final are. Well, if I want to know how high it goes, that means I sort of want to know the distance or the displacement from here where it started to up here at the top. So why don't I make the bottom my initial, the top my final, and then I could just solve for D. That would give me the height. So let's make a note of that. We'll call this initial, and we'll call this final. Okay. So if that's my initial and that's my final, what do I know? Well, I know it was kicked at 15. So after it leaves the person's foot, it is going 15 meters per second. And that's in the upward direction, so it's very intentionally a positive number. I know that at the very top of its trajectory, right up here, when it's as high as it's going to go, when it's not going any higher, its speed is going to be 0. So VF will be 0. And because this football is close to Earth's surface, because it's not a really light thing that takes up tons of space like a balloon or a piece of paper, it'll feel negligible air resistance. It's also not going hundreds of kilometers an hour. And because we're looking at the time when it's left the person's foot, so it's not touching the foot, it's not touching the ground, it's got nothing on it to push it one way or another, so it will feel no force except gravity. Therefore, we can say its acceleration is 9.8 meters per second squared down. Or instead of down, we'll just make this negative. So now that I know those three things, I can solve for D. That's the thing I'm trying to find. How high does it go? Remember, D is displacement. It's a straight arrow from start to finish. So in order to find D here, I got to pick an equation that has D but doesn't have T. And I think the one to go with is going to be our third equation from the big three. This guy here. If I rearrange it to isolate D, then I'm going to get this. And if I plug numbers in, VF is 0, VI is positive 15, and A is negative 9.8. And that gives me an answer of 11.48, or if I round it to 3 sig figs, I get 11.5 meters. And I get a positive number, meaning my displacement is up, which makes sense, because if displacement is a straight arrow from initial to final, that arrow would have to be going up in this situation. So my answer to the question, how high does it go, is going to be 11.5 meters. All right. Now, next question is, what is the total hang time? By hang time, I mean the total amount of time it's in the air, on the way up and on the way down. And also, what is its velocity when it hits the ground? Well, let's tackle those two questions in the space below. I'm going to redraw my diagram because there's a couple of points I want to make here. Actually, let's copy the diagram we already have. Okay. Well, if I want to know the total hang time, right, that's the total time it's in the air. That's the time up and the time down. How am I going to solve this? Well, one way I could do it is look at the way up, find the time, and then look at the way down, find that time, and add them both together. Let's take that approach. So for the way up, I'm going to use the same initial and final that I had before. There's my initial. And here is my final. So on the way up, I'm going to have VF, VI, A, D, and T. And I want to look at the way down as well. So for the way down, this is going to be the start, and this is going to be the finish. So my initial and final will be reversed. And on the way down, just like on the way up, I'm going to have a VF, a VI, an A, a D, and a T. So let's figure out what all of these guys are. On my way up, the F is at the top. So the ball has stopped for an instant. VF is going to be 0. VI is how fast the ball was going when it was finished being kicked. And that, I believe we can check the question, was 15 meters per second. Upwards, so positive. A is negative 9.8 meters per second squared. We already discussed why that would be. And we actually know D on the way up too, because that's what we found over here. That was my 11.5 meters. And I should probably record it, if in case I use that number later, I should probably record more than just the 3 sig figs I recorded before. So I think the full number was 11.48. And I can make a note to myself up here that 11.5, if I record more sig figs, was 11.48. Remember, we try to get in the habit of rounding to 3 sig figs if it's a final answer, but keeping 4, or even better would be 5, for numbers that we might use again later. Okay, so if I want to find the total hang time, we said I was going to find time up, time down, and add them. So let's see if we can find the time up now. Well, I have basically everything I need for the way up except the time. So I can use any equation I want that has time in it to solve for time. And I think probably the easiest one would be our first one. VF equals VI plus A T. Rearranging this to solve for T, I get VF minus VI divided by A equals T. And then if I plug stuff in there, I get 0 for VF, positive 15 for VI, negative 9.8 for A. And if I go through all of that, I get 1.53 seconds is my time, rounded to 3 sig figs. Okay, so that's the time it takes the ball to go up. How about on the way down? Well, let's see what we know here. On the way down, my initial is right at the top, where it has just stopped for an instant and gravity's starting to pull it down again. So my velocity there, my VI, is going to be 0. My VF, that's sort of how fast it's going down here when it hits the ground. Not sure what that's going to be. I know my A is going to be negative 9.8. Again, why do I know that? Well, the ball is close to Earth's surface, right? It's, it's 11.5 meters off the ground, but we said even when we're at the top of Mount Everest, there's a small difference in Earth's gravitational pull, but it's minor. It's, 1% or less. So as long as we're less than the top of Mount Everest, we say we're close to Earth's surface. It experiences negligible air resistance. Again, it's not something that takes up a lot of space and is really light, like a balloon or a piece of paper. So there's not much air resistance. And because it's not touching anything else, it doesn't have anything on it that can, propel it in a direction or the other. It feels no force except gravity. And that's why we can say its acceleration is negative 9.8. And again, one thing I want to draw to your attention here, on the way up and on the way down, acceleration was negative 9.8. Common mistake students often make at this point is they think acceleration will be positive when it's going up and negative when it's going down. No, velocity is positive when it's going up and negative when it's going down. But the direction of acceleration isn't the direction you're going. It's the direction you're being pulled or pushed. And whether you're going up or down, this ball here we're talking about, whether it's going up or down, it's always being pulled by gravity, and gravity always pulls down. So that's why acceleration is negative in both of these cases. And since it was 11.48 meters to go up, if we're coming down the same distance, that can be 11.48 meters as well. Only because we're moving down, it'll now be negative. Remember, displacement is a straight arrow from initial to final. So while that was an upwards arrow on the left-hand side, a straight arrow from initial to final is going down on the right-hand side. That's why we have a positive d on the way up and a negative d on the way down. So, knowing all of those things, if I'm trying to find t, I want a formula that has t but doesn't have VF. That's kind of tricky. There is one, d equals VIT plus 1/2 AT squared, but that one has two t's in it and one of them squared, so it's hard to isolate t. So I think the easier way to do this might be just to find VI first and then use it to find t. So let's do that. Finding VF first. Oops, that's not the equation I want. I want an equation that has VF but not T. So this guy will work. Okay. So if I solve that, I get that VF is 15.0 meters per second. Actually, I get plus or minus 15.0 meters per second. Remember, whenever I take the square root in order to get rid of a square, I have to remember the answer can be plus or minus. So I actually have to pick which one of these is correct. Because I'm trying to solve for the velocity of the object on its way down here, I think its velocity at the end, the f, should be negative. So it's the negative one I'm going to pick. So 15 meters per second. Oh, I'll keep that decimal in there. Okay. So that's the VF. The goal here was to find VF so that I could use it to find T. But actually, I've inadvertently solved for part of the problem. The question asked me for the velocity when it hits the ground. That's this guy. The way I've drawn it here, there is actually like a little bit of a gap between the ground and where final is. I think that's pretty negligible compared to how high this thing is going. And I probably drew this soccer player as having a kick that's quite high off the ground. In reality, it's going to be released from the kick almost exactly at the ground. So these two heights are basically exactly the same, and we consider both of them as being basically on the ground. Okay, so let's go ahead now that we have our VF and use it to find our T. And the simplest equation for finding T then is going to be the same one we used over here. VF equals VI plus AT. Here, note that because I decided that VF had to be 15 down, remember I wasn't sure from the math whether it was plus or minus, so I selected down. I selected negative one. That means I have to use the negative one for VF over here. And if I plug that in, I get to 3 sig figs 1.53 seconds is the time. So there's a couple interesting things to point out here. On the way up, I found a time of 1.53 seconds. On the way down, I found a time of 1.53 seconds. This is not a fluke. This happens with every question you'd ever do like this. And so there's a bit of a moral to this story. And that moral is, as long as we are on level ground, meaning the ball hits from basically the same height that it was released from, the time to go up is equal to the time to come down. And the other thing that kind of popped up that you may not have noticed is the velocity. We tried to find VF on the way down, the velocity when the ball got back to the height it started from, when it hit the ground. And we figured out it was 15.0 meters per second squared down. Well, how high was the ball kicked to start with? That was given to us in the question, and it was 15 meters per second. So the ball was kicked up with 15 meters per second. It went up, 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 slowed down, lost a bunch of speed, turned around, sped up, sped up, sped up, gained a bunch of speed, and when it got back to the height it started from, it had the exact same speed. Again, this is not a fluke. This will happen every time as long as you're on level ground. You're ending at the same height you start from. So this is important too. The speed at release be the same as the speed at catch. Or sometimes we can just say speed up equals speed down. But I find that can be confusing because it sometimes makes people think that there's one speed the whole way up and one speed the whole way down. The speed's changing the whole time, but if we just look at two instants, right here and right here, the speed at those two instants will be the same. So let's just make sure we've actually answered our question. What is the total hang time? Well, let's write that down. That's the total time it's in the air. So that's the time up plus the time down, which will give us .06 seconds. And the other thing we wanted to know was the velocity when it hits the ground, which we found. Velocity at ground. That was this guy here, 15.0 meters per second down. The exact same as the velocity it was kicked with. So those are our answers to this problem. Okay, so key idea here is as long as we're close to Earth's surface, as long as we're not an object that's going to feel tons of air resistance, and as long as there's nothing pushing on us, nothing touching us, no force except gravity, we can always use this as our acceleration. And that's what we did in every scenario here in this problem. Other things to remember is when you're looking at a problem where there's a bunch of things you have to find, it can be useful to break it up into a few parts. In our case, we did the way up, which had an initial and a final, and then the way down, which had its own initial and final. Those were different from before. And then just pay attention to directions, to plus and negative signs. And then we learned these two tips. If you've got an object going up and down under the force of gravity, the time it takes to go up is going to be the same as the time it takes to go down. And the speed at a certain point on the way up will be this. It'll have the same speed when it reaches that same point on the way down. These two facts are useful. If you remember these, feel free to use them. They can make solving problems a lot faster. Consider them shortcuts. But if you forget them, that's okay, because we were still able to solve this problem when we didn't know these two facts until the very end. So as long as you're able to follow on with everything we did here, you don't actually need to remember these two facts, but it can be useful.